Good evening. I'm Karin Taylor. I am Program Director of the General Society of Mechanics and Tradesmen of the City of New York, and it is, on behalf of the Society, it is my great pleasure to welcome you here this evening. The Labour and Literature and Landmark Lectures are supported in part by public funds from the New York City Department of Cultural Affairs in partnership with the City Council. I also wanted to express our thanks to New York Landmarks Conservancy, our partner for tonight's program, and for all the landmark lectures, for their help and support. For those of you who may be less familiar with the General Society, a very brief introduction. The Society was founded in 1785, and we've actually just celebrated our 230th anniversary this year. This is actually our 5th home in New York City. So today, this organization continues to serve and improve the quality of life for the people of New York City through several particular programs. These include our tuition-free Mechanics Institute, the General Society Library, of course, of which you're in this evening, and our nearly 200-year-old lecture series, of course, of which this lecture is part of this evening. You will find an informational postcard that provides background information on your seat, and if you're interested in library membership information, you will find that on the front table. The 2016 Landmark Lecture Series, entitled Preserving the Recent Past, is curated by Lisa Easton, a partner in the New York-based architecture and historic preservation firm, Easton Architects. It is now my great pleasure to introduce Lisa Easton to you, who will then introduce our speaker. Lisa.
Thank you, Karin. Good evening, everyone. Welcome. Thank you for coming. I'm honored to be a part of the General Society of Mechanics and Tradesmen's 2016 Labor, Literature, and Landmarks Lecture Series. I always love that tongue twister. And when asked to create the 4-part Landmarks Lecture Series, I wanted to bring together a group of people whose experience captures the essence of preserving our treasured landmarks, from technology of materials and methodology to advancement and historic research. This year's theme for the Landmark Lecture Series is Preserving the Recent Past, as Karin has mentioned, which will highlight some of our most valuable architectural resources from the modern movement. Tonight, I'm honored to introduce Glenn Boornazian, Architectural Conservator and President of Integrated Conservation Resources and Integrated Conservation Contracting. In 1988, recognizing that the market for historic preservation services was highly fragmented, Glenn started what would become Integrated Conservation Resources, or ICR as we all know it, and Integrated Conservation Contracting, ICC, in order to combine investigative architectural conservation services with high-quality conservation and restoration contracting. Today, as president of both companies, Glenn draws on his extensive knowledge of building materials conservation to provide technical services for historic buildings and monuments. His expertise includes specialized conditions investigation, materials testing, analysis and assessment, and the implementation of treatment recommendations. After studying at Columbia University's graduate program in historic preservation, Glenn served as staff conservator for the Center for Preservation Research at Columbia University and director of restoration for the Nantucket Historical Association. He has served as adjunct assistant professor at Columbia University's graduate program from 1996 to 2002 and speaks widely on historic preservation. Currently, Glenn serves on the boards of the Historic House Trust, Fort Tryon Park Trust, and the University of Florida College of Design, Construction, and Planning Board of Advocates for the historic preservation programs. This evening, Glenn will be speaking about the role of architectural conservation and how it plays in the development of the conservation programs for mid-century modern structures, specifically through his work including the Saarinen TWA Terminal, Frank Lloyd Wright's Guggenheim Museum, and the buildings located on the campus of the United Nations here in New York City. It is my great pleasure to introduce to you tonight Glenn Boornazian.
Thank you and good evening. It's a pleasure to be here, and thank you, Lisa, and the Conservancy and the General Society of Mechanics. Just a little change. I'm going to really focus on Frank Lloyd Wright's Guggenheim and the TWA building. If I can get through those two, then maybe we can touch on a few other things as well. But as Lisa said, I'm the president and founder of Integrated Conservation Resources and Integrated Conservation Contracting, where we both design and implement conservation programs for historic buildings and monuments. I thought first, as a way of introduction, that I would tell you a little bit about what drew me to this field, quickly run through a few of our projects, describe what an architectural conservation program is to us, and then show you how we applied our approach to develop procedures to address the challenges at mid-century modern sites, again, of the Guggenheim and Saarinen's Flight Center. Both these images show each building just as their exterior shells were almost complete. The image of the Guggenheim was taken about June of 1959, and the image of the TWA Flight Center sometime in the summer of 1961. And what's interesting to note is that these two buildings are approximately 2 years apart from each other. Looking back, I find what has drawn me to this field is a deep appreciation of what creative people can design combined with what a talented group of people can build with their hands. When the best of what we can do in both these fields comes together, what results can be quite awe-inspiring. Over the last 29 years, we at both ICR and ICC have been extremely fortunate to have had the opportunity to work at some of these great sites. Although periods of construction and geographical location vary tremendously, the same basic human creative spirit to design and build is there. Because time is limited this evening, I'll just focus on one of these sites. And this is quite a departure from mid-century modern, but it will give you a little bit of an idea of the range of what we deal with. So working closely with the World Monuments Fund, we've been in charge of 4 of their temple sites at Angkor in Cambodia. And working closely with the Cambodian government, as well as UNESCO, we have been designing these conservation programs, training and implementing the work with approximately 130 people ranging from architects, engineers, archaeologists, business administrators, and team leaders and craftspeople. The largest project of the 4 is Phnom Penh, and it was the first temple built by the Khmers when they came to the site of Angkor. This is the general site of the ancient city of Angkor. This is Angkor Wat, and this is Phnom Penh. This is Phnom Penh, or a small section of it, when the French came to the site in the 1940s and started clearing the jungle off the temple complex. And this is in the 1950s when the French had finished their work. And I think what's just amazing to note is that this, like I said, was a hill. Over there, it's called a mountain because there's not very many of them. But it continued up like this. And in the 10th century, 9th century actually, the Khmers basically took 25% of the top of this mountain off. They exposed the live rock in the middle, and they carved that live rock to serve as the foundation for the structure that's there and that you see now. So that today, what we're doing is we're working on stabilizing the bedrock that I was telling you about. We're waterproofing the temple complex. We're conserving the stonework. And we are reconstructing some areas of loss in a way that aesthetically blends in with some of the older stonework. So here's one section where you can see where the live rock that I was describing to you has actually fallen away. The facade stone have been removed. This is being stabilized and reconstructed. And there's a lot of other work happening there as well, but I thought it was an interesting project to compare to what we'll focus on soon, which is mid-century modern buildings. So as another brief introduction, architectural conservation to me is the science related to building materials. The roots of the field can be found in fine arts conservation. A major difference, however, is that architectural conservators have to design programs for materials that are exposed to the elements, whereas fine arts objects can be placed in controlled environments. Architects, over the course of time, have designed details into systems, even here at Penobakang, or in the previous slide, into their buildings that work in balance and to protect the building materials from exposure to the environments. Yet no matter what, short of moving a building inside, wind, rain, freeze-thaw cycles, and salt crystallization, among other things, are all active pressures that constantly keep the exposed portion of a structure in a state of decay. Understanding the mechanisms of that decay, designing programs that do not accelerate that decay, and managing that decay is a part of our work. As architectural conservators, we design our projects based on a certain set of goals. We try to save as much original material as possible or as practical. We respect the design intent of the architect and/or craftspeople who were involved in the design and construction of a building. We design materials and methods that are both physically and aesthetically compatible with the original construction materials. We do this through a series of specific tasks. Through archival research, sorry, that's a little small, material and condition surveys, laboratory testing, field testing, the implementation of probes, non-destructive evaluation, and carrying out of mock-ups of potential treatment options. And as I go through some of these projects, you'll see this process over and over. This evening, I will focus on our work regarding the design and implementation of architectural programs for mid-century modern structures. It is very exciting and a bit different for us to work on these more contemporary structures that are relatively young. One reason is that there is a lot more information available in terms of original drawings, specifications, construction photographs, letters, even videos of design professionals who speak in detail about their design goals and describe issues of concern that took place during the design, during construction, and shortly after completion. In fact, some of the people are still alive who were involved in the design and construction of some of these buildings. And in almost all of the 30 years that I've been involved in this field, I think that this phase of work at TWA is the first time that I have ever had the chance to sit in the same room and talk with a person who was intimately involved with the design and construction of TWA. Alba Tour, who was the lead structural engineer at Alman & Whitney, who was the creative force behind helping Saarinen realize his design in such a sculptural way, is actually still alive, and I've had the chance to meet with him. His knowledge of what took place has helped our team tremendously, and to actually meet a person who was there, who can describe in detail the process, makes this work even more exciting to us. He has been kind enough to share some of his images with us, and I'll be sharing some of those with you tonight. Although Frank Lloyd Wright and Saarinen were from different generations, they shared some important things in common. They were dedicated to making a break from architects of the past. They experimented on a grand scale. Their buildings were a blend of sculpture and architecture. They used the fluid nature of cement to achieve their sculptural forms. And Frank Lloyd Wright was dedicated to what he called organic architecture. And similarly, Eero Saarinen had a strong conviction that a building, as he put it, is only one thing. This is a quote, that the inside and outside should sing with the same message. Every detail was studied and worked to the end like parts of a great, giant, unified piece of sculpture. I will just mention two other ICR mid-century modern projects briefly: the United Nations campus in New York, where construction was complete in 1952, and where we focused on the development of conservation programs, and we actually did the quality control of the work as it was being implemented on the stonework of these facades. And we've also had the honor to be involved with Edward Durrell Stone's embassy in New Delhi. Work on this project began for Stone in 1956 and was completed in 1959. ICR worked closely with the U.S. State Department, Weissman Freddie Architects, and Richard Southwick, who will be talking here in a week or two, who's the Director of Historic Preservation at Beyer Blinder Bell, to compile an in-depth architectural materials section of what's known as a Historic Structures Report. There he is, Richard Southwick. So, this is the way the exterior of the Guggenheim appeared in May or June of 1959. The application of the elastomeric coating known by the product name Cocoon was almost completely applied. So here you can see that the concrete, or this, had been completely encapsulated with this elastomeric coating. I think there's just one piece right here that still is left to be done. 3 different types of concrete were used to construct the building. Spray-applied gunite was used to construct the ramp walls, and plywood forms were constructed. Armatures of steel, rebar, steel tees were installed, and I'll show you more about that. So basically, these plywood forms were constructed. The metal armature was inserted and built inside, and then from the inside, the contractor sprayed the gunite from the inside out, so up against the plywood forms, which became a large problem for Wright. So poured in place lightweight concrete was used for the construction of the apron slabs, which go right underneath the gunite walls. And a typical poured in place stone concrete was used for the remainder of the building. There are a few other elements which we should review, and if you were here at Nancy Hudson's presentation, she probably reviewed some of these as well, but just quickly, these are going to show up in the talk and in the description of what some of the cause and effect problems were. So the vertical support web walls with their embedded T's at the web and gunite interface. So you can see that these web walls are structural, and I'll show you some pictures of them as the building goes up, but they run every 30 degrees, I think. And they also have a embedded metal T at their end, which is encapsulated in the gunite when the gunite was sprayed. There are also these intermediate T's that are completely encapsulated in the gunite wall. And the gunite wall is only 5 inches thick. So if you think about something 5 inches thick, with all that steel I was talking about before and these T's, it's sort of a recipe for a little time bomb. If that steel isn't protected, it oxidizes, it grows, and it damages the concrete. So here I just want to point out a typical gunite ramp wall in section, and the intermediate, again, as I just pointed out, metal T's. Wright had talked a lot with a number of people, and everyone informed him that the ramp walls especially required expansion joints. Otherwise, there would be cracks forming, and the incorporation of an expansion joint means there has to be a vertical line in that, which would have appeared in these gunite walls, and Wright just could not sleep at night thinking that his organic form would have a vertical line in it, so no expansion joints. William Short was Wright's supervising field architect and was dedicated to documenting the structure in all phases of construction. He would go on to the roof of the building at the south end of the site and take photographs from almost the same location on a regular basis. The amount of documentation on this building is massive, and when I first saw this, I thought the museum should collect all these photographs, put them together, and make a flip book, because you could just watch the building appear before your eyes. So I selected a series of these images to give you a quick glimpse of what I had seen, and they're not very clear, but it's fun to watch. So here's Fifth Avenue, and there's, I guess I can't remember, 88th Street, and we're right at grade here. So a tremendous amount of work has had to have taken place just to get this slab up to grade. But these next series of, 8, 10 slides will start to show you the work that had to take place. And I don't really want to stop too much because it will, interrupt the sequence. But what's amazing to do is watch where all of these temporary ramps are constructed, because that's where the men use their wheelbarrows and actually move the cement around. And they didn't have these big hoppers that had pneumatic tubes that could pump massive amounts of concrete. They had a crane that lifted a bucket that dropped about 55 gallons of cement, and then wheelbarrows took this material all over the site. So you can start to imagine that the time it would take to construct such a building was massive, and the same with TWA. So the steel work coming up. Now the center is coming up. The way they built this was, the way they could keep all these dimensions was they had this center pole in the middle, and that was the only way that they felt that they knew where they were at any given time. And that's that. I just want to go back one slide, I think. No, maybe two. So here, you can see those web walls. And they extend not only down and come up through each floor, but at the top, they come up this way and around and back down again. And the gunite walls are not there yet. You can see here's the end of the web wall, and the gunite wall form hasn't even been applied at this time. So some post-pour concerns were the presence of these form board marks, which I was telling you about, which were so obvious and exposed on the exposed surface of the gunite after the plywood forms were removed. You can sort of see them here, but I'll show you a better image. These marks were of such a concern to Wright, as they interrupted the organic smooth surface finish that he was dedicated to achieving, that he instructed the contractor, without asking the owner, to remove them. And here you can see the contractor starting to remove them. This was such a difficult and expensive task that the work was halted, and the marks were never completely removed. As a result, these marks have become a very important part, actually, of the construction history of the building. And here is a picture taken before the project that we worked on. So this is a buildup of about 11 or 12 coats of paint, and you can see those board marks coming through really, really strong. If we had the time, there are some amazing letters that go back between Wright and the contractor that, in only a way he could, described why it was so important that that contractor remove those form marks. Anyway, there were also locations of the concrete surface that failed during construction. And I'm just using these arrows to point out to you sections where, when the form was removed, concrete fell off. So this was not an easy job. The contractor who was chosen to do the work was really a road contractor who had done a tremendous amount of concrete work. And I think one of the things that we can compare is the level of sophistication that was applied at TWA versus here. They're both grand experiments, but it seems to me from what we've done so far that the work at TWA is much more controlled. There are experts in every aspect of the work there that helped Saarinen achieve his goals. So to continue on with the Guggenheim, this project team was made up of the owner, obviously. The Paratus Group was the owner's rep. Wank Adams Slavin was the architect, Robert Silman the structural engineer, and we were the architectural conservators. And it was an interesting arrangement. It wasn't a typical situation where we had contracts with the architect. Everyone had a separate contract with the owner, and it was done, I think, for a way to create an interesting dynamic that I think in the end actually worked out very, very well, but getting used to it for some of us was not so easy. So since the first step was to remove all of the applied coatings, some of which had failed and others which had reached the end of their useful life, understanding the original color and changes over time were required. Representative coating samples were taken, mounted, and viewed under magnification. The stratigraphy of these was, for all intents and purposes, was the same. So this is a typical paint stratigraphy. I think we took 100 samples. I don't think any of them were different. Certainly the original coating wasn't different. There might have been other coatings that were applied over time. But here is I think this is a gunite sample, so here's a gunite surface. There's a primer that was applied. This is the original cocoon. You can see it's a high, thick build, elastomeric coating, and it was very unusual for its day in 1959. And that was applied, I said, like in 1959. This set of layers, we think, were applied between 1960 and 1991, and we do know that this layer here was applied during the 1992 restoration when the addition was added. This image is a technical sheet or a color chart of the cocoon from the company Hollingshed that provided cocoon, and you can see that Frank Lloyd Wright says OK, FLW, approved, approved, approved. So there was really no question of what he was looking for. And if there was any doubt that he was there while the material was being applied, this photograph was not manipulated by anyone. So numerous products were tested to develop an effective way of removing the coating. And after we determined an appropriate procedure, full-scale removal was implemented. And the original concrete on all surface of the structure were now exposed for the first time since 1959. And this was done for numerous reasons. One, it had to be done to reapply a new coating in such a way that would have a long life. But also, the whole design team felt that we needed to see the surface in its entirety, to be able to compare and contrast the conditions, which enabled us to prioritize them and then measure them and develop specific repairs for specific conditions. So here is the west elevation and the result of one of the mapping campaigns, which was extremely effective and really helped us separate the different types of conditions, then helped us develop certain repairs, and really started to help organize what was a very overwhelming surface when we first started to see it. So here's a drawing that's indicating the placement of specific movement sensors that Nancy, I'm sure, reviewed with you in her presentation. But to us, the results of this testing helped our conservation effort by allowing us to know the amount of movement that we were dealing with in representative locations and design specific compatible repairs for each type of movement or each amount of movement. And I'll tell you why in a little bit. In addition, representative core samples of the different types of concrete were also taken and subjected to a number of tests. On the left, you can see a core with the exposed surface at the left, and in the image on the right, an indicating stain showing the depth of carbonation, which is the alteration of material due to exposure, which, as you can see here, or I will point out, is not very deep. So here's a core, here's the cocoon on the surface, and here is a different core in section with a stain applied to see what sections of the material had been altered. And by that, it's really pH. If concrete is not exposed to the elements, the pH will be high. As it's exposed more and more to the elements, the pH drops, and the effect on the building gets much more serious as it goes deeper and deeper in. Because once the pH drops, the rebar is in an environment where it can oxidize a lot easier and then start to cause a significant amount of problems. So the fact that Wright found, or someone found, that cocoon is really, we all thought, what sort of saved that building for the amount of time that it had been in place, which was from 1959 to 2007. So samples were also submitted for petrography and compressive strength tests. Among other attributes, the petrography helped to identify each of the constituent parts and their ratios within each mix. We used that information to design test samples, which we exposed to accelerated weathering, to an accelerated weathering test program, and in the design of potential other repairs. Probes were carried out in strategic locations to determine the extent of decay. And here you can see, again, we're back to the web wall T. There's the T that's there. Here's corrosion at an intermediate T. And I think Nancy must have talked to you about the fact that a major problem was that on the 6th floor ramp, these rebar were not continuous, and all of a sudden the structural design of the system started to scare a lot of structural engineers. and then some rebar corrosion. So, this again started to help us start to formulate a sense of the priorities that we were being faced with. So we designed an in-house accelerated weathering program that would expose potential treatments to the types of conditions that they would be exposed to in the New York City environment. After a great deal of research and evaluations, reviewing about 20 manufacturers, 6 were chosen and were included in the initial phase of this program. And 2 actually made it through the accelerated weathering program, and we took those and we did mock-ups on site and monitored them so that we could feel comfortable about making a final decision. So here in this picture, you can see this is the mix. We used the petrography for to come up with the mixture for. They're going into molds. They're being cured in a way that we felt was required to try to achieve the same sorts of physical strength as the actual material on the building was at. We tried to think about how we could mimic the different cracks and areas that required patching to also include that in the program. So here we tried to create a smaller crack, here a little bit of a larger crack. We also drilled holes in some of these samples and through the cracks so that we could put patching materials in there. And here on the right, you can see the patching material being applied. On the left, now some of the crack filling, expandable crack filling materials are being installed. And after that's done, some of the elastomeric coatings are being applied. A QUV weatherometer was used to expose test panels to accelerated conditions of ultraviolet light, condensation, and associated heat, and thermal shock as a result of applying cooled water in a spray to those samples. The first round of tests exposed samples to 1,500 hours of exposure, and samples were evaluated every 500 hours. The cycle for freeze-thaw testing was 16 hours thawing in 22 degrees centigrade water, followed by 8 hours of freezing in minus 22 degrees centigrade air. Changes in test panel appearance were noted after each cycle and were photographed approximately every 6th cycle. The tests were run for 30 cycles. I guess what I'm trying to show you here is that maybe it's clear, we did not want to rely on any product manufacturers. We wanted to understand what the needs were, we wanted to understand what we thought was required, and then we wanted to make sure that what manufacturers said was actually something that we could rely on. And one last test I'm going to show you, we ran a few others, is something known as water vapor transmission rate testing. We basically took samples of the cement, we took the coatings that I had shown you before, we put them into a vial with deionized water, and so the only way that this water could actually escape is through the whole sample, and all of them are put into a environmentally controlled tank, and which is at a low humidity, and each one is weighed every 24 hours, and then the weight loss is basically based on the loss of the water, and then we can do a mathematical formula to calculate the water vapor transmission rate and then compare them to everything else. So what was absolutely shocking to all of us was that after not so rigorous a test, we started to see the crack fillers expand. They started to break the coatings started to bubble, and this one was from the QUV. From the freeze-thaw tests, the others the same thing, larger bubbles, different ways of expanding. And this is just one of these optical illusions. Those aren't going in, they're actually coming out. But again, if we had gone to onto a manufacturer, it could have been problematic. So a few other tests where we wanted to test the adhesion of the different coatings, and we modified a standard test procedure for that. And we also wanted to monitor color and color change through each aspect of the testing procedure. So we utilized a spectrophotometer for that. So for our on-site mock-ups, as I said before, the two final product systems were carried out and left in place to be monitored and measured on the building. The idea with this repair was that we were going to create expansion joints at the gunite wall tees, where the building determined they were required, but Wright didn't want them to be. The size of the opening would be determined based on the amount of measured movement in a given location from those sensors, and careful consideration was given to preventing the repair from affecting the shape of the exposed surface coating as the building expanded and contracted. This condition was viewed in different light forms, including raking light, as we were trying to prevent the joint filler from becoming concave or convex, depending on if the size of the joint was smaller or wider based on temperature. All of this was done so that the surface would appear smooth, uninterrupted, and organic as Wright had intended it. The section of this is the gunite wall in section. This is the T. We've removed in this section the damaged gunite. We have treated the T with rust inhibitors and coatings. Then we've applied our patch, and I'll show you this in a second. And then we filled, depending on the amount of movement, we filled this from the T forward with a specific material, and then depending on the amount of movement, we filled the end with another material, which all got coated with an elastomeric coating. And all of them have to work in unison. We can't have any separation. If we do, we'll end up with the same results as we saw coming out of the accelerated weathering. So I'm going to run through this now in the field. I think you can see the materials being removed. A metal plate is installed and held in place by these shims, and the craftsman is installing the patch on one side. And then a dense foam material is inserted, and to keep the space of the joint size that we want, and then the left side is installed. If there are any form marks that were in the abutting original material, those form marks were mimicked and came through. So when, that building being round as it is, the sun always shines on it in a raking fashion, and seeing any alteration to that surface would be extremely easy. So then the crack fillers were installed in different ways, and then the coating was applied. So here's coating being applied, continuing to be applied, and here are the sensors that will be in place as this coating is exposed to the environment for the next, I think it was almost a year. Again, basically the same thing, a completed mock-up on site on both images. So once this whole laboratory and field-based testing was completed, we chose a particular system. And in the end, it was really not a difficult task. This one product, or this one system of products, what they said they were, and it was very exciting for us to find something that we really felt confident that we could rely on to do what we expected them to do. So the contractor worked with us, or the manufacturer worked with us to train people here to apply it properly, which was no easy task. And no one was going to apply anything to the building until their mock-ups were approved. And then finally, just a few before and after pictures, and they're not so exciting because everything gets kind of painted. But here's a condition on the apron slab, so we're looking up at the apron slab before and after. Here's a horizontal crack and some paint failure before and after. Here's one of the web wall tees that were broken with a monitor going. I don't know what that is. Before and after. The intermediate tee on a ramp wall. And the completed building. So this was in 2009, and today we continue to work with the Guggenheim. We actually just wrote a grant with them to the Getty in the hopes that we could start to look at the building from a maintenance point of view and design a long-term cyclical maintenance program. Obviously, doing this sort of work is a wonderful first step, but it's not the end. Maintaining a building like this is extremely important to protect the investment and also all of the hard work that went into it. So, okay, TWA. Arrow Saarinen received this commission for the TWA project in 1956. Wright was already working hard on the Guggenheim. And this advertisement that came out at about the time of completion of the building in '62 described how the building expresses the excitement of jet travel. And I know Richard will be talking about the birth and death and re-erection of the terminal. But I thought it was important to talk to you a little bit about what went into that design, and really in terms of materials, because knowing that would help us understand again, what the priorities were and how we might deal with them. So I'm just going to describe to you, this is after the roof was, or the shell was finished, but I wanted to let you know that the roof was made up of 4 separate shells, all poured with lightweight concrete, separated by skylights, which also doubled as locations to absorb expansion and contraction. Each of the 4 roof sections that you see are supported at 2 points by the 4 buttresses, bringing the load of each to the ground, and all 4 shells are connected as they touch at the center of the roof, which you can see. And here's one of the buttress, so that you can see how it's reaching out and grabbing a point at each shell, so each shell is grabbed at each end. The innovation, experimentation, and risk that took place here was on all fronts: design, engineering, and construction. The design team worked on this phase of work on the design team currently working on the conservation phase of this phase of the work at the TWA Flight Center involved the owner, MCR Development, Bayer Blinderbell with Richard, and Arab engineers as well as ICR. With no computers to generate 3-dimensional images, Saarinen worked with large-scale models generating dozens for TWA project alone. So here is Saarinen with, again, one of the models. And if you look on the walls, he's got numerous different roofing designs to use and put in place as part of the process. Once a model was complete, cameras were inserted inside of it, and images were taken to give the design team a sense of space. And once that was done, draftsmen actually climbed inside to take measurements. So here is a model and a camera installed, as I said, and photographs taken. It's actually quite amazing, the feeling that you have. It's almost like you're there. And it gave Saarinen the ability, I think, and his team to really get a sense of what this building was going to be. And again, since there were no computers, taking measurements from these and doing design documents and drawings was probably more challenging than building the building. So here is someone working hard, taking measurements. And one of the drawings, I know Richard will show more of, that was coming out of Saarinen's office. This is the interior stair, both in section and in plan, and with all of the curves and all of the details. And when you start to see the interior, which I'm sure Richard will show you, it is literally sculpture. There's no two ways about it. And here's an example of a structural drawing that was supervised by Abator and coming out of Ahman and Whitney's office. Close-up examination of this plan shows exact locations of the rebar and steel layout for each of the 4 shells. And you can zoom in on these drawings and see tremendous amounts of information, but the precision with which these rebar were designed, the size, the shape, the contours, the overlap, the way they were connected, everything was thought out, and numerous books of calculations were devised to make sure that, or to try to make sure that this worked. Many drawings in section were also created, and here is just one of them. Basically, there was a drawing, every 3 feet they cut a section through the roof, and at those sections you can see that, again, the steel is laid out exactly how they wanted it. So how did they build it? I was fascinated. I don't know new buildings. I'm just starting to get to know them. So to do it, they had to construct a steel scaffolding frame that could support the roof. And once that frame started to take on the shape of what they wanted it to become, they had screw jacks at the top that lifted wooden beams into place that they could start to build this lower section of the form. So this is basically the ceiling that you would look at from below if the insulation wasn't there. Basically, the level of craftsmanship here was absolutely essential, because if there was a mistake here, the mistake would show in the concrete, and if the mistake showed in the concrete, the lines that Saarinen were looking for would not be there. And just one little anecdote, the engineer wanted to create the peaks as they were curved, and he was absolutely dead set against that. He said, when I fly in on an airplane, I want to be able to look down and see an edge there. So, we're talking about levels of detail that are very well understood and focused. So these pictures are from Abator, and this is actually his daughter standing on the roof. But you can start to see the level of detail and the precision with which this shell was built. They almost look like hulls of ships upside down. And so here would be one of the wings, or one of the shells. Here another. This being the hump in between them with the skylight on top. After the formwork was complete, the rebar that we saw in the structural drawings was all laid out and carefully set in place. And in final review and approval of the rebar placement was carried out, and everything was checked and double-checked and triple-checked, because once the cement pour began, there was no turning back. And each separate shell had to be one monolithic pour. They could not stop. So that was one good reason they had the skylights, because they didn't have to pour the whole roof at one time. They could at least do one shell at one time. But with those 55-gallon buckets of cement coming up, the pour of the larger shells was about 30 hours each. And actually, here they're starting, and they had to do this by day, and here's one of those buckets, and they had to do this by night. So a critical moment after the cure of the concrete was the slow and careful removal of the scaffolding support system below. The concrete was cured by keeping it wet for almost 3 weeks, and no scaffolding was moved until the compressive strength of the concrete reached 4,000 psi. They had cores that they were measuring and testing, and nobody, I'm told, touched anything until that happened. And because of some concrete damage, I think, that happened at the United Terminal, that was happening simultaneously, the Port Authority got very nervous about this building all of a sudden. And they got so concerned that they hired a specialist from NYU who attached strain gauges to different sections of the rebar and were taking measurements to make sure that the loads were one way when the rebar was not loaded. They were measured when the rebar was loaded, and then they were measuring very carefully as the scaffolding was being removed. They also had points on the building that they were shooting constantly to make sure that nothing was moving. So here is an image just after removal of the support of the scaffolding, and the following is a quote from Abatur. "It took a considerable amount of interaction with the architect to impose some structural logic or discipline on it. It was a creature which started out wild and needed to be tamed and domesticated." And some close-up images after the forms were being removed. It really is quite amazing, much more like sculpture than any building I know. And it's just amazing for me to think about the risks that people were taking at that time. I have to move a little faster. So here's just an overall image. And as I was saying before, Saarinen was designing every detail of this building. This is a color schedule. I could go on and on with the details that were being designed, but what was great about this was that the kind of specifications we were seeing are the kinds that architects, or good architects, generate today. And this one here, CC concrete color, was specified for every location that a person would see if they were standing inside the terminal in a main space. To verify that, we took samples, and they were there. Here's the substrate. There's the original finish, substrate, original finish, substrate here, original finish. And if you are lucky and find some historic photographs, and I know this is black and white and at night, but here is the concrete exposed, and there is the interior. And if you look even in different lighting situations, you can see the similarity of color. Here, the pier, which is stone concrete, the roof, lightweight concrete, the roof of the wing coming and turning under, and the stucco underneath, all harmonize and are similar. So for us, our initial job was to quickly try to find locations underneath the existing coatings that might show signs of distress and damage, as there was no way that we were going to be able to remove the coating in the design phase. So we worked with an engineering firm who specializes in non-destructive evaluation, Atkinson Nolan, who, using microwave radar and thermography, infrared thermography, helped us try to find some hot spots through the coatings. So I just want to show you, here's the one of the tubes being constructed, and here's one of Atkinson Nolan's thermographic images. Quite amazing what it can show in terms of, if you're lucky, what the actual substrate materials are and what their layout is. So we start to shoot different sections of the roofs of the building, and if you look at this particular image, you can start to see the rebar showing through. And it's showing through because the temperature of that rebar is different than the temperature of the surrounding materials. And that only happened in one or two locations, and we felt that if we were seeing that might have meant that rebar is closer to the surface, that if it is closer to the surface, water could have penetrated down a little bit. If it did, it could have changed the pH, could have oxidized the rebar, and we could have had a problem there. So that was a place that we decided to go. And we removed, this is the coating, we removed the coating, we exposed the original concrete here, and we did a bit of a condition survey. These little red marks indicate the location of micro cracks, and these are areas where we conducted a few probes. As we cut through, let me go back a second, as we cut through these and started to dig down, we saw that they were only on the surface. They didn't radiate down into the substrate at all, even though we thought they might have been associated with the rebar. And when we went down, I'm sorry for the image, but when we went down to the rebar, it was exactly the dimension down that was stated in the contract documents, and it looked as clean and nice, I'm sure, as the day it was installed. So if it's one thing that we're seeing different here, I think the precision that was used to create manage and pour this concrete on this building has allowed it to stand up so much better. And we're still trying to pinpoint it, but we do not think coatings were applied to the surface of the building for quite a number of years after its construction. So even another item that shows, or another way they're showing how dense that material actually is. So cores from representative locations were taken and are currently being subjected to compressive strength tests and petrographic analysis. We will use that data in similar ways that we did at Guggenheim to design compatible treatments, repairs, and potential coatings. And that will be another presentation at another day. And thank you very much for your attention. So I think they would like us to have questions and answers. Well, questions, I don't know about the answers.
You mentioned Frank Lloyd Wright having problems with the plywood.
Well, I don't think he had problems with the plywood. I think he had problems with the fact that the plywood was showing after it was removed in the gunite. But yeah, and he felt his reputation was at stake, and because he was 91 years old, this was an extremely important project to him. I think actually both architects saw this as almost the culmination of their careers at this point. And certainly for Frank Lloyd Wright, every detail was extremely important. And I don't have the letters with me, I wish I did, but he would write to George Cohen, the contractor, and say something like, you know, your reputation is at stake, I'm sure you understand this, but other people that I used to do my gunite would never settle for something like this. You know, if you want to stay in business, which I'm sure you want to do, you know, all of that lovely talk. But it was staggering for Wright. It was a game changer for him. And literally that concrete set up, and there was no way that they were going to get those form marks out. And what was also interesting is that now they become part of the history of the building. So question is, like, when you do restore the building, do you remove the form marks because Frank Lloyd Wright wanted them removed? And no, you don't. I don't think the New York Landmarks Commission doesn't, and I think many, you know, international organizations feel the same way, that the design intent and the actual object that was created are two different things.
But in the Frank Lloyd Wright building, the form marks were not meant to be seen. You could see it in the slide that you showed where the piece of plywood was on a diagonal, which I couldn't believe. Whereas here, in the Saarinen building, the form marks were they were part of the architecture, right?
Yeah, yeah.
So they were really carefully considered.
Yeah. Yeah.
On the lower parts where it's exposed, correct?
Definitely, right. So on the, I don't know what you call them, where the roof makes a return and comes up, on that return and on the underneath sections, you see all the form marks. And I agree with you. I mean, that was something that was considered and desired. But you're right, Frank Lloyd Wright did not want those. So an aesthetic that an architect chose. You know, the board marks that on the gunite walls at Guggenheim they deform as well. So the surface isn't smooth, the surface isn't continuous or organic. And you know, I think the architect on Saarinen's, from Saarinen's perspective, he got what he wanted, and Wright didn't.
In the previous lecture, the woman did mention the contractor's response saying that the work was done in the best methods we knew and best methods possible. So in your opinion, was it a failure of the contractor, or was Frank Lloyd Wright mistaken in hoping that they wouldn't be seen, the form marks?
I think it was, I think I think it could have been done better. I think, understanding that the forms have to be a specific way, and the minute concrete is poured in there, that's what you're going to get. So making sure that every aspect of that form is as precise as you want that concrete to be is the level of detail that you need to be taking out in the field. So I would think that it could have been. I know it could have been done better. You can look at in France, Corbusier was doing work in Marseille. The quality of that concrete is 1,000 times better than that. So from a craft point of view, not an issue.
You mentioned in the testing that you did of the patching materials that you found some products that were not up to their manufacturer's claims, and some, or one, that was. I'm curious if you published that information anywhere.
Yeah, I think we have published it, but the company, I have no problem telling you, is a company by the name of Mape, and they are an Italian company that is owned by a family. It's a large company, probably one of the largest in Italy, and I didn't even know them before the project started. And we basically set up this filter system of, what was working and not working. And Mape was the only one that sort of fell out at the bottom of that filter system that looked like they could be a potential, or potentially reach the goals that we were setting. And we never told the manufacturers what the project was. We just tried to keep it as independent and as objective as possible. And when we finally met these people from Mape, you could just see their quality control. They put millions of euros a year into product development. They are precision oriented. They are quality control. They're quality control in making their products are like, I was there one time, they have buckets going by on lines, things are being tested, they're being knocked off the assembly line. I mean, they're testing everything that comes in trucks, or every additive that comes in trucks to sites. I mean, it's really the only way that you can run a company like that, it seems to me, and be able to say that here are the results and here is the mechanical qualities of our product, and we back that up 100%. So if you're interested, I can show you some of the articles that we published. Okay.
In 1959, I was working at the airport, Idlewild at that time, and I was working at KLM, and there was rumors while TWA was being built that they were having terrible time with pouring the concrete, and that the rumor was that they had to pour the concrete 2 or 3 times, and I don't know whether the rumor was true or not.
I don't know. Well, I don't know. Richard, do you know?
There was actually a hurricane that came through during one part of the pour, and one of the pours was actually suspended because of a very severe weather. But as Glenn was saying, it was a precision work, and it did go nonstop, and that was the only hiccup.
Glenn, first I'd like to thank you very much for a really beautiful presentation.
Sure.
I've always loved the buildings, and now I understand them better, so thank you for that.
Sure, you're welcome.
I'm wondering if your company and your genius was in setting the benchmark for all of this different type of reconstruction and renovation work, or is it standard of the industry at this point?
I think, excuse me, when we started at Guggenheim in 2004, what was amazing about the project was that the client saw the building as a part of their collection. So they allowed us to treat it as if it was an object, and they allowed us to do the testing that was required on each of the different concrete types that were there to understand them better and to do the kind of work that I showed you. So yeah, I think in a way what we designed was one of the first times that concrete and different types of concrete were looked at in that way. And as a result, I think, people are using that. And there's more concrete conservation that's being done now. So what's also fabulous, though, too, is that the building wants, or the building, the Guggenheim Museum wants to go and actually start looking at the building again from a maintenance point of view. What went right, what went wrong, what do we have to do to get it up to a maintainable standard, and then what kind of a cyclical maintenance program do we have to put in place to do this. And that would be published if we get the grant.
Glenn, on behalf of us all here this evening and the General Society, I'd like to thank you for such a comprehensive, detailed, and fascinating presentation. We are deeply grateful to you for the huge amount of work that must have gone into this presentation. So on behalf of us all, thank you very much.
Sure. You're welcome.
And this is something I'm not normally able to say, but we're going to have more of Glenn in 3 weeks' time. So another date for your diary will be Tuesday, May the 10th. On that date, Glenn is going to be part of our Artisan lecture series and is going to talk about conservation from the artisan perspective. Is that a good overview? So I just want to mention that. But as is our normal, on these occasions, we would like to make a presentation as a small token of our appreciation.
Hello.
And this is Meg Stanton, our program assistant. So this is a citation. Glenn Boornazian, Integrated Conservation Resources, the development of architectural conservation programs for mid-century modern structures. So we would like you to have a citation from the General Society of Mechanics and Tradesmen of the City of New York in recognition of your contribution this evening. So thank you very much. Yeah. And we would also like to present you with lifetime membership to the General Society Library. And finally, a little memento of the evening.
Thank you very much. It was a pleasure.
It's our absolute pleasure.